In this video, we are going to continue our midterm 1 review by looking at an error example. So the problem says, suppose that the third derivative of f evaluated at c is equal to negative 3 cubed over c minus 5 squared plus 270. And we are approximating the original function f using a second-ordered Taylor polynomial centered at 0 by evaluating it at x equals 6. If we are approximating a number gamma, so that's what this symbol is. This is the Greek letter gamma. So we're approximating some unknown number that we're calling gamma. And our approximation is that gamma is about 123. Find an interval that contains gamma. Part A, using alternating series error, and leave your answer unsimplified. So the first thing that I would need to do is, to be able to use alternating series error, I know that the absolute value of the error is less than or equal to the absolute value of the next term. So we need to know what that next term is, and usually we look to the series to determine what that is. So I need to remember the form of a Taylor polynomial. So Taylor polynomial looks like I have the sum from 0 to infinity, and then in this case it's centered at 0, so we'd have an x to the n, and then in front of that we're going to have a coefficient, and the formula for the coefficient is you take your nth derivative and you evaluate it at the center point, which in this case is 0, and then that gets divided by n factorial. So the number that we're plugging into this parentheses, that's a. That's the fact that a equals 0. All right. So since we are using a second order polynomial for our approximation, that means the next term occurs when n equals 3. Because that would be the next term for a second order Taylor polynomial. Okay, so if we plug in n equals 3, what would that next term be? We would get the third derivative of f evaluated at 0, and then we would be plugging in, what are we plugging in for x? Well, we're approximating at x equals 6, so we'd get 6 to the n, and n is 3 here, and then divided by n factorial, which would be 3 factorial. So now, plugging in 0 into that third derivative, we end up getting negative 3 cubed at the top, so negative 3 cubed, and then we get 0 minus 5 squared plus 270 times 6 cubed all over 3 factorial. So we have this. So now let's continue to simplify. I'm going to do that at the top of the top of the page. So what I'll do first is I'll bring this thing that's in this denominator down here to simplify it. So doing that simplification, we get this. All right, so now taking this absolute value, this negative goes away, and we'll get 3 cubed times 6 cubed on the top. On the denominator, negative 5 squared is 25. 25 added to 270. That's 295. So we get 295 times 3 factorial. So that is an upper bound for our error. So the interval that we'd get for gamma, and what gamma is in between, would be our approximation, 123 minus something, and then 123 plus something. And what this something is, so whatever this thing is and this thing is the upper bound that we got for the error, which is 3 cubed, 6 cubed over 295 times 3 factorial, and same thing here, 3 cubed, 6 cubed over 295 times 3 factorial, and that is our interval. Alrighty, now let's do the same problem but using Taylor remainder error. And again, I want to leave our answer unsimplified. So pause the video for about 2 minutes to try this problem. For 3, 2, 1, pause the video. Pause the video for about 2 minutes to try this. That might not be enough time to finish the problem, but hopefully it's enough time to get started and think about what the key steps would be. Alright, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to try this. So let's talk about it together. So with Taylor remainder error, the absolute value of the error is less than or equal to m times x minus a to the n plus 1 over n plus 1 factorial, where, so what's m? Well, the n plus first derivative of a function evaluated at c needs to be less than or equal to m for all. So I'll write something here, but before I write down what it is, let's state what some of these values are for x and a and n. So x was the number I'm plugging in to evaluate my function and get my approximation. And the problem told me that's 6. A was the center point, and the problem told me that's 0. And then n is the order of the Taylor polynomial that we used to get our approximation. And the problem told me that was 2. It told me we were using a second order Taylor polynomial. Okay, so let's finish this sentence. So now, the n plus first derivative of f evaluated at c, and absolute values is less than or equal to m for all values of c that are between a and x. In this case, that means c is in the interval from 0 to 6. So in this case, 0 is the a, in this case, 6 is the x. All right. So the first thing that we do in these Taylor remainder problems is, once we have this set up, once we remind ourselves what's the formula for the error, is we find m. Okay, so it was our third derivative. So once we plug in n, and we look at the n plus first derivative, we'll get the third derivative of f. The third derivative of f evaluated at c, the problem tells me is negative 3 cubed over c minus 5 squared plus 270. So that's what the problem tells me it is. So now we need to take the absolute value of this. So we got to take the absolute value of this third derivative evaluated at c. And doing that, we'll get the absolute value of negative 3 cubed on the top. On the denominator, we get c minus 5 squared plus 270. Okay, so negative 3 cubed, once we absolute value that, gives us 27. On the denominator, we have c minus 5 squared plus 270. Because of the squared, I know that c minus 5 squared is not going to be negative. It's non-negative. And then adding 270 to that makes the whole thing positive. So the denominator is not negative, it's non-negative. So I don't need to put an absolute value around it. Okay, so I need to know what this is less than or equal to. Okay. Alrighty, so here is how we can think about that. I need to sort of find an upper bound for this fraction. And to do that, I want to make this fraction larger. I need to make it larger and put whatever is larger than it in this space here. So to make this fraction larger, we need to minimize the denominator, because the smaller the denominator gets, the larger the whole fraction gets, and that's what I want. Minimize the denominator on the interval that we care about in our problem, which in this problem is 0 to 6, because that's what it says c is in between. Okay, so I could either do this algebraically and think about the fact that, wait, c minus 5 squared is always greater than or equal to 0. So c minus 5 squared is always greater than or equal to 0. And the smallest that gets is at 5. The other way, and that tells me that this happens at c equals 5, because that's when c minus 5 squared actually equals 0. That's the smallest it'll get. But I can also do this graphically. The denominator here is simple enough to graph. The graph of that is actually, so it's a quadratic function. The graph is a parabola. And I see the leading coefficient is positive. Let me start with the vertex, actually. The vertex would be 5, 270. 5, 270 is the vertex. And it's an upward-facing parabola. So the graph would look something like this. And we want to know where the minimum of that is on the interval from 0 to 6. So 0 is definitely a whole lot further away from that vertex point. So that corresponds to, and let's draw the y value at 6. So where 0 is, that's actually the largest this parabola gets on this interval. And I'm just going to shade in the part of the parabola we care about. But the min happens here. The min at c equals 5. And we want to minimize the denominator, because that makes the fraction the largest possible. Okay, so the numerator, let's keep it as 270. But if we plug in 5 into the denominator will become 270. And what does this simplify to? This becomes 1 over 10, and that is what m will be. Alrighty, so now let's take that and let's plug it into our formula for the error. Alright, so the error in absolute values is less than or equal to m times x minus a, so 6 minus 0, to the n plus 1, which is 3, divided by n plus 1 factorial, 3 factorial. And now plugging in what m is into this, we know m is 1/10, so we'd end up with 6 cubed on top. On the bottom, the 10 would go there, that's coming from this 1/10, and then times 3 factorial. And I don't need an absolute value around this because this is already positive. And that's our error right there. So if we want our interval for what gamma is in between, we take that approximation. The problem told me that gamma is approximately 123. And then I need to subtract and add this upper bound for the error. Because the error is how much gamma could be off when we approximated 123. So how much gamma is actually off of 123? The most it could be off is this upper bound for error. So I subtract 6 cubed over 10 times 3 factorial, and then I add 6 cubed divided by 10 times 3 factorial. And that is our interval. And the problem told me that I should leave my answer unsimplified, so I want to leave it here rather than use a calculator.